Hi, I'm Mark Barsamian. In this video, I'll be discussing partition numbers and critical numbers. This is material from section 4.1 of the book. The corresponding homework for this video is this collection of 3 exercises from section 4.1. The asterisk on this problem 31 indicates that that problem is not in the MyLab system, but it is in the book and it's worth doing, and we'll do a similar problem in this video. We're going to use some old ideas in this section. The important concept of continuity from section 2.3. Remember that to say that a function is continuous at a particular x value means that it passes these 3 tests. The limit exists at that x value, the y value exists at that x value, and the numbers from those 2 tests agree. That is, the value of the limit equals the value that's the y value. If the function fails any of those 3 tests, then we say that it's not continuous at that x value. And recall the definition of partition number from that same section. A real number x is called a partition number for a function f if f is discontinuous at x or if f of x equals 0. Now, we've seen that partition numbers for a function are important because they're the only x values where the function f of x can change sign. And we see that in order to find the partition numbers, we have to find all the x values that cause f of x to be 0 and all the x values where f of x is discontinuous by failing any of the 3 continuity tests. Now, today we're going to be interested in finding partition numbers for f prime. So in section 4.1 so far, we've already seen that it's useful to determine the sign behavior of f prime because information about the sign behavior of f prime can be translated into information about the increasing and decreasing behavior of, this should say, f of x. So again, information about the sign behavior of f prime translates into information about the increasing, decreasing behavior of f of x. Now, in order to determine the sign behavior of f prime, we have to make a sign chart for f prime. And in order to make a sign chart for f prime, we have to start by finding the partition numbers for f prime of x. So that would mean that we would have to find all the x values that cause f prime of x to be 0, and all the x values where f prime of x is discontinuous by failing any of the 3 continuity tests. Now, it turns out that for the functions that we study in this course, the job of finding the partition numbers for f prime is made slightly simpler because of the kinds of functions that we study. In this course, we only work with functions f of x whose derivatives, f prime of x, will only fail continuity test 1 at x values where they also fail continuity test 2. That means that in this course, the only x values where f prime of x will fail to be continuous will be the x values where f prime of x fails to exist. That's continuity test 2. F prime of x would have to exist for f prime of x to be continuous at a particular x value. So the only functions we'll be working with will be functions where the derivative f prime has the property that the only places where f prime fails to be continuous will be the places where f prime fails to exist. So for these functions, you don't really have to do the 3-part continuity test on f prime. You only have to find the places where f prime fails to exist. So that allows us to give a simpler definition of a partition number for f prime of x. A partition number for f prime of x is a number x equals c that causes either f prime of x to be 0 or f prime of x to not exist. Now, before going on, remember why we're interested in the partition numbers for f prime. The partition numbers for f prime are the only x values where f prime can change sign. And so on the intervals between the partition numbers for f prime of x, the sign of f prime does not change. And so therefore, the increasing, decreasing behavior of f of x does not change as well. Now, we were led to think about partition numbers for f prime of x by wanting to find the intervals where f of x is increasing and decreasing. Those will always be the intervals between the partition numbers for f prime of x. It turns out that it's useful to scrutinize the partition numbers for f prime of x more carefully. We'll be interested in finding out which partition numbers for f prime also satisfy an additional requirement. Those that do satisfy this additional requirement will be called critical numbers for f of x. So here's the definition of a critical number for f of x. It is a number, x equals c, that satisfies these two requirements. The first requirement is that the number x equals c has to be a partition number for f prime. But there's a second requirement, that is this: the number x equals c is in the domain of f of x. So if we want to translate those two underlying things into what they really mean, the number x equals c has to satisfy this: f prime parentheses c equals 0, or f prime parentheses c does not exist. That's the requirement for x equals c being a partition number for f prime. And then the second requirement is this: f of c has to exist. We'll do 3 examples today. They have different functions, but the same tasks. These 3 functions, one is a polynomial function, one is a rational function, and the third function is a power function with a fractional exponent. For all 3 examples, we'll be doing these 3 things: find f prime of x, find the partition numbers for f prime of x, and find the critical numbers for f of x. All right, example 1. This is similar to 4.1, number 27. F of x is this cubic polynomial. Question A, find f prime of x. So there I've found the derivative, and notice that I went ahead and factored it because we know that in question B, when we're finding the partition numbers for f prime of x, we're going to want to set the derivative equal to 0 and solve for x. So for that, it'll be useful to have the factored form. All right, let's do question B now. Find the partition numbers for f prime of x. Now remember what that means. A partition number for f prime of x is a number x equals c such that f prime parentheses c equals 0, or f prime parentheses c does not exist. Well, notice that our f prime of x is a polynomial, so there are no bad x values. There are no x values that cause f prime of x to not exist. So the only partition numbers for f prime of x will be the numbers that are the solution to the equation f prime of x equals 0. So we solve that equation and we find the solutions are x equals -5 and x equals 5. So those x values are the partition numbers for f prime of x. Now for question C, we have to find the critical numbers for f of x. Let's go back up and review that definition. A critical number for a function is a number x equals c that is a partition number for f prime and also is in the domain of the function. The critical numbers for f prime of x have to be partition numbers for f prime of x, and they must also be numbers that are in the domain of f of x. Well, we see that the only candidates are these two numbers. Those are the only numbers that satisfy the first requirement. They're partition numbers for f prime. Now, what about the second requirement? Numbers have to be in the domain of f of x. Well, remember that f of x is a polynomial. So its domain is all real numbers. So that tells us that these two x values that are partition numbers for f prime are automatically critical numbers for f. So our answer to question C is that same pair of numbers, x equals -5 and x equals 5. Let's go on to the next example. F of x equals 1 over x minus 5. This is similar to book exercise 4.1, number 29. So question A, find f prime of x. Notice that f of x looks like a quotient. It's presented as a quotient. That might make you think that you have to use the quotient rule, but realize that there's a much smarter way of finding its derivative. Rewrite the function as something in parentheses raised to a power. Now find the derivative of that expression. So there's a long calculation of f prime of x. Notice that I recognize the form of a nested function, so I used the chain rule. I did the chain rule details over here on the side. Notice that I made a mistake early on. I wrote this as x minus 1, and then I corrected it later. Notice that the outer function is a power function. So to find its derivative, I used the power rule. And then I wrote the final result in positive exponent form. So there's our derivative. Now we have to find the partition numbers. We have to find the x values that cause f prime to be 0 or f prime to be undefined. We'll do that on the next page. Okay, the partition numbers, remember, are x values that cause f prime to be undefined or that cause f prime to be 0. Notice right away that there is one x value that causes f prime to be undefined. That would be x equals 5. So the question is now, are there any other partition numbers? That is, are there any x values that cause f prime of x to be 0? Well, to answer that, notice that f prime of x is a fraction. And remember that a fraction is only 0 when the numerator is 0 and the denominator is not 0. But our fraction has a numerator that's the number -1. It will never be 0. So the takeaway is that there are no x values that will cause f prime of x to be 0. So the only partition number for f prime of x is x equals 5. All right, let's go on. There's a part C. Remember, part C is to find the critical numbers for f of x. Well, let's remember what those are. A critical number for f of x is a number that's a partition number for f prime and is also in the domain of f. Well, notice that we found a partition number for f prime. It's this green number, x equals 5. Now the question is that in the domain of the function f of x? Let's go back up and look at the function f of x. F of x is this function. The number x equals 5 is not in the domain of f of x. So x equals 5 cannot be a critical number for f of x. So our conclusion is that f of x has no critical numbers. Let's go on. Example 3. This is similar to 4.1, number 31. F of x is this power function with a rational exponent. So question A is find f prime of x. So we found the derivative using the power rule with n equals 1/5, and then we converted to positive exponent form. Now let's go on to question B. Question B says find the partition numbers for f prime of x. Those are the numbers that cause f prime of x to be undefined or f prime of x to be 0. Now notice that f prime of x is a fraction, and the numerator of that fraction is the number 1. The numerator will never be 0, so f prime of x will never be 0. Now, are there any x values that cause f prime of x to be undefined? Well, notice that f prime parentheses 0 does not exist, so therefore x equals 0 is the only partition number of f prime of x. Now let's go on and answer question C. We have to find the critical numbers for f of x. Let's go back up and review the definition. We're looking for x values that are partition numbers for f prime and that are also in the domain of f of x. So we have only one x value to investigate, x equals 0. We just have to see if that's in the domain of f of x. So f of 0 is just the number 0. That does exist. So that means that x equals 0 is in the domain. So x equals 0 is a critical number for f of x. That's the end of this example, and that's the end of the video. Thank you.